Welcome to Hired in IT. Our mission is simple: help you build the skills that employers actually want. Whether you're trying to land your first IT job, switch careers, earn a promotion, or increase your salary, we're here to help. Every video is thoroughly researched and designed to make complex IT topics easy to understand. If there's an IT topic you'd like us to cover, leave a comment below. We may turn your suggestion into our next video, turning IT knowledge into career opportunities. It's 2 a.m. and the support queue just tripled because the customer chatbot promised refunds it can't actually issue. Somewhere between the model and the order database, the AI gave away money that isn't there. The person on call to untangle that mess is the one who wired the model into the product in the first place. Later in this video, we'll call that job by its actual name and show exactly what they do. By the end of this video, you'll be able to state what an AI engineer actually does on a Tuesday, tell 5 overlapping AI titles apart without mixing them up, and know the first 5 skills to start building tonight. 3 outcomes, no fluff. An AI engineer is a software professional who builds and ships production AI systems. Sometimes that means taking a traditional machine learning model and putting it behind an API. Increasingly, it also means building applications around foundation models and large language models. An AI engineer might connect an LLM to company documents using retrieval-augmented generation, give an AI agent access to tools and APIs, build structured outputs, evaluate model responses, add safety guardrails, and monitor the system after deployment. They usually aren't inventing a new neural network architecture from scratch. Instead, they're asking, which model should we use? What context does it need? Which tools should it be allowed to call? How do we evaluate whether its answers are actually good? How do we make it secure, reliable, fast, and affordable? And how do we integrate all of that into the product customers actually use? That's the role in one sentence. Research creates new AI capabilities. AI engineering turns those capabilities into reliable production systems. A data scientist just spent 3 months training a fraud model that scores 99% in tests. But it only runs inside a Jupyter notebook on her laptop. She reruns a cell. It prints a number. Nothing else happens. The business can't put that notebook in front of customers. The AI engineer closes that gap, wrapping the model in an API, wiring it into an app, and getting it in front of the person who actually needs the answer. AI engineers and machine learning engineers overlap heavily, so don't treat them as completely separate jobs. Both may write Python, deploy models, build APIs, work with cloud infrastructure, monitor production systems, and optimize performance. The difference is usually emphasis. A machine learning engineer often goes deeper into the traditional ML lifecycle, training pipelines, feature pipelines, model optimization, model serving, inference infrastructure, and ML ops. An AI engineer, especially in modern generative AI teams, often works more broadly around foundation models and applications, LLM APIs, RAG, embeddings, vector search, tool calling, agents, evaluations, guardrails, and application integration. But job titles vary. At one company, the person building a RAG system may be called an AI engineer. At another, ML engineer. At another, applied AI engineer. So don't memorize titles. Look at the actual work. If the job focuses heavily on training and operating ML models, it leans ML engineering. If it focuses heavily on turning existing AI models into useful applications and business systems, it leans AI engineering. And in many companies, one person does both. Quick recall check. Can you spot the difference? If you picture this job as all model building, reset that picture. A typical week spans coding and integration, cleaning data and building pipelines, deployment and monitoring, debugging or on-call, and meetings. The exact split varies by team, sprint, and company. What's usually missing? Most weeks, nobody trains a brand new model from scratch. A clinic uploads 20,000 patient records and wants to build a system that helps predict missed appointments. Before anyone trains or calls a model, the data needs attention. Are the records complete? Are important fields missing? Are dates formatted consistently? Are categories represented consistently? Are there duplicate records? Is sensitive information being handled appropriately? And is the data actually suitable for the problem we're trying to solve? That's data preparation. An AI engineer may work with data engineers, data scientists, or analysts on this step rather than owning every part personally. But the production lesson is the same. AI doesn't fix bad input data automatically. Before building the intelligent part of the system, somebody has to make the data trustworthy enough for the system to use. Here's a better way to think about data cleaning. Don't begin by blindly deleting every row with a missing value. Start by inspecting the data. Which columns contain missing values? How much data is missing? Why might it be missing? Is that record unusable? Could the missing value be handled another way? And would deleting those records distort the dataset? The same thinking applies to categories. A machine learning pipeline may need categorical values transformed into a representation the model can use. Python libraries such as Pandas and scikit-learn can help with that process. But the important skill isn't memorizing one dropner command, it's understanding the sequence. Inspect, clean, validate, transform. Then verify that your pre-processing behaves the same way when new production data arrives. Because a beautifully trained model sitting behind an inconsistent data pipeline is still a broken system. Feature engineering means turning raw information into signals a machine learning model can use effectively. Suppose we're predicting whether a patient will miss an appointment. Raw age may be useful. Appointment history may be useful. The number of previous missed appointments may be useful. How far in advance the appointment was scheduled might be useful. But you shouldn't simply throw every available column into the model. Some fields may add noise. Some may leak information the model wouldn't actually know at prediction time. Some may create privacy or fairness concerns. And categorical values need to be encoded appropriately for the model and problem you're working with. That's why feature engineering isn't turn every word into a number. It's choose and transform information that helps the model solve the problem without introducing unnecessary noise, leakage, or risk. And for modern LLM systems, the equivalent question becomes, what context should the model receive to make a good decision? Different technology, same engineering principle. Give the system the right information. Quick recall check. Before you can train a model on clinic no-show data, what two data tasks have to happen first? Pause if you need to. If you said cleaning missing values and engineering features, encoding categories, scaling numbers, you're on track. Garbage in, garbage out. Here's the part almost everyone gets wrong. A model that scores brilliantly inside a Jupyter notebook can fall over the moment real traffic hits it. The notebook isn't the product. Model deployment is what turns that trained artifact into a live API endpoint an app can call, not just running it manually when you're at the keyboard. Until it's deployed, it's a science experiment, not a feature. This is the Python pattern that bridges research and production. Instead of running a cell inside the notebook, you send a real network request to the deployed model's endpoint. The payload carries the exact input fields the model trained on: age, gender, visit history, and the response comes back as JSON, a plain text format for sending structured data between programs. This request and response pattern is the basis of REST APIs. That's the entire move from local experiment to live feature. Cloud platforms offer a managed deployment path for models. In a typical console, you select a pre-trained model, create an endpoint, give it a name your app can call, and send a sample request to confirm it returns a prediction. The platform handles much of the infrastructure, servers, scaling, updates, while your job is configuring the model, wiring the endpoint, and connecting it to your application. The exact labels differ by provider, so verify the current console flow before you click. A customer service chatbot can't just answer from the model's imagination. It has to look up the caller's order history in the CRM before saying anything. That connection, model, database, front-end, and third-party services, is system integration. And the classic beginner mistake is shipping that AI feature with no fallback. If the model call fails, the bot should say, "I can't access orders right now," not invent a refund. Quick check. You have a live model API. Is that the same as the AI feature being integrated into your product? No. Deployment makes the model reachable. Integration wires it into the actual app, databases, and user flow. One is plumbing, the other is the user experience. A recommendation widget that takes 4 seconds to answer doesn't feel slow. It feels broken. Users bounce. Performance optimization is the work of making AI fast enough to keep people around. Profiling to find where the time actually goes, caching repeat answers, load balancing traffic across model replicas, and splitting heavy jobs across machines. Most teams only need one of these to start seeing a real difference. When an AI application feels slow, don't immediately throw more servers at it. First, find out where the latency actually comes from. Maybe the model is slow. Maybe your retrieval query is slow. Maybe you're sending 20,000 tokens when the model only needs 2,000. Maybe the application is making 3 tool calls sequentially that could run in parallel. Maybe you're repeatedly computing something that could safely be cached. Different bottlenecks require different fixes. For some workloads, traditional caching works well. For LLM applications, you might also evaluate prompt caching or semantic caching when the workload and correctness requirements make that appropriate. Other optimizations can include using a smaller or faster model, reducing unnecessary context, streaming the response, batching requests, optimizing retrieval, running independent tool calls in parallel, or routing simple requests to cheaper models. The engineering rule is measure first, optimize the actual bottleneck second, because the fastest optimization is the one that fixes the part of your system that's actually slow. Getting the AI into production isn't the finish line. It's when the difficult part starts. For a traditional predictive model, you might monitor whether the input data has changed, whether accuracy is dropping, and whether retraining is necessary. For an LLM application, the questions expand. Is the model giving correct answers? Is it hallucinating? Is retrieval returning useful context? Are tool calls succeeding? Are users constantly triggering the fallback? How much does each request cost? How many tokens are we consuming? How long does the response take? And did the new prompt or model version actually make the application better? This is why production AI requires more than uptime monitoring. Your API can return HTTP 200 all day, while the AI gives terrible answers. A healthy server does not automatically mean a healthy AI system. So, what does an AI engineer monitor? Start with traditional application metrics: availability, latency, errors, throughput, then add AI-specific signals. For predictive ML systems, that may include prediction quality, data drift, model performance, and retraining indicators. For LLM applications, you may monitor evaluation scores, retrieval quality, tool call success and failure rates, fallback rates, token usage, cost per request, safety or policy violations, user feedback, and the quality of responses across important test cases. The exact metrics depend on the application. But here's the principle: don't monitor only whether the AI responded. Monitor whether it responded well. That's the difference between application monitoring and AI observability. What a modern AI application actually looks like. A loan approval model passed every accuracy test. Then a reviewer found it was rejecting otherwise identical applicants from one zip code. Responsible AI means thinking about fairness, privacy, and security before a model touches real users. That includes reviewing data for bias, minimizing the personal information you send, and keeping enough detail to understand decisions later. The common trap is assuming an accurate model is automatically safe. It isn't. You've probably seen the title Prompt Engineer. Standalone prompt engineering roles do exist, but don't make the mistake of thinking prompt engineering always represents a completely separate career from AI engineering. Prompt engineering is increasingly one skill inside a broader AI development workflow. An AI engineer may spend part of the day improving system instructions, then test structured outputs, then modify retrieval, then change a tool definition, then run an evaluation suite to see whether any of those changes actually improve the system. The prompt matters, but so do the model, context, retrieval, tools, application logic, evaluations, and guardrails around it. So think of prompt engineering as an important applied AI skill, not necessarily the entire job. Here's the distinction worth remembering. Prompt engineering focuses on how you communicate instructions, context, examples, and constraints to a model. AI engineering owns a much larger system. An AI engineer may absolutely write and optimize prompts, but they may also build RAG pipelines, connect vector search, define tools the model can call, create structured outputs, build APIs, implement authentication, deploy the application, add evaluations, monitor latency and cost, and debug failures in production. So prompt engineering fits inside many AI engineering workflows. The better career question isn't, should I learn prompt engineering or AI engineering? It's, how does prompt and context engineering fit into the larger production AI stack? Learn the skill, then learn everything required to ship it safely. AI engineering sits in the middle of several overlapping careers. A data scientist may focus more heavily on experiments, analysis, statistics, and modeling. A machine learning engineer may go deeper into training pipelines, model serving, inference infrastructure, and MLOps. A software engineer may focus on the application architecture, APIs, front-end, back-end, and product experience around the AI. An AI or ML platform engineer may build the infrastructure that lets many teams deploy, evaluate, secure, and monitor AI systems consistently. And an applied AI engineer may spend most of the day building applications around foundation models, RAG, agents, and tools. Then there's automation. AI engineers may use those same technologies to automate internal workflows, classifying support tickets, extracting information from documents, researching cases, generating reports, or coordinating multi-step business processes. The titles overlap, so when you're reading job postings, don't obsess over the title. Read the responsibilities and ask, which part of the AI lifecycle does this job actually own? If you're starting today, build your skills in layers. First, Python and software fundamentals. Learn functions, data structures, packages, error handling, Git, testing, and how to work with APIs. Second, LLM APIs and model fundamentals. Learn how to call models, compare models, control outputs, manage context, and work with structured responses. Third, RAG, embeddings, and retrieval. Learn how documents become searchable context and how retrieval quality affects the final answer. Fourth, tools, function calling, and agents. Learn how models interact with APIs and external systems instead of only generating text. Fifth, deployment and cloud. Containerize or deploy an AI application and learn the basics of authentication, secrets, scaling, and networking. Sixth, evaluation and observability. Measure quality, latency, failures, token usage, cost, and user outcomes. And seventh, security and guardrails. Learn prompt injection risks, data exposure, authorization, tool permissions, and how to limit what an AI system is allowed to do. You don't need to master all 7 before building something. Learn one layer, build, then add the next. Here's the working stack that lines up with the job we just walked through. First, Python. Know the requests and pandas libraries, not just the syntax. Second, REST APIs. Build one and call one. Third, cloud model deployment. Pick SageMaker, Vertex AI, or Azure ML and ship a tiny model on a free tier. Fourth, data cleaning and feature basics. Handle missing values and encode categories. Fifth, monitoring and logging. Attach logs and one alert to anything you deploy. That portfolio shows an employer you can ship, not just train. Here's a practical 30-day starting plan. Week 1, Python plus LLM APIs. Write Python code that sends a request to a model and receives a response. Then make the response structured instead of just printing free-form text. Week 2, tool calling. Give the model access to one safe function, maybe weather data, a calculator, or a small database lookup. Learn how the model requests a tool and how your application controls the execution. Week 3, build a small RAG application. Take a handful of documents, create embeddings, store them in a searchable system, retrieve relevant passages, and give that context to the model before it answers. Now, your AI can answer from your own data. Week 4. Make it production-minded. Deploy the application. Add logging. Track latency and errors. Measure token usage and cost. Create a small evaluation set with questions the system should answer correctly. Then test it after every major change. At the end of 30 days, don't just say, "I learned AI." Show an application that uses a model, retrieval, tools, deployment, and evaluation. That's portfolio evidence. Here's the whole AI engineer role in 3 ideas. First, the model is only one component. Production AI also needs data, retrieval, APIs, tools, application logic, security, deployment, evaluations, and monitoring. Second, AI engineering is about making AI useful and reliable. A demo that works 5 times isn't enough. The system has to work when real users ask unexpected questions, APIs fail, documents change, traffic spikes, and costs start accumulating. And third, job titles overlap. AI engineer, applied AI engineer, ML engineer, software engineer, and AI platform engineer may own different parts of the same lifecycle depending on the company. So don't build your career around memorizing a job title. Build the skills required to ship production AI systems. Then prove those skills with projects you can explain. What problem did you solve? Which model did you choose? How did retrieval work? Which tools could the model call? How did you evaluate quality? How did you secure it? And how did you monitor it? If you can build a system like that and explain your engineering decisions clearly, you're much better prepared to compete for applied AI engineering opportunities. The whole picture in 3 sentences. An AI engineer applies existing models in production. The job is integration and deployment, not inventing new algorithms. Second, the work runs through data, deployment, integration, monitoring, and performance. Skip anyone, and the system breaks. Third, related jobs sit around this role, each emphasizing one part of the lifecycle, such as prompting, model research, product features, or automation. Learn the production skills, and you're hireable. Download the free IT career roadmap from the description. It maps the order to build these skills without wasting weeks. Then this week, do one thing. Open a Python file, call a public large language model API, and print the response. That single request separates watching from doing. Remember, careers aren't built by watching videos. They're built by applying what you learn. Pick one thing from today's lesson. Build it, document it, and share it. That's how you get hired. Thanks for watching Hired in IT, where we're turning IT knowledge into career opportunities.